Hello, everybody. My name is Mihalis Mathioudakis, and on behalf of the governing board of the Hellenic Astronomical Society, I'm welcoming you to our today's colloquium. We are very pleased and honored to have today Professor Mihalis Mathioudakis from Queens University of Belfast in Northern Ireland as our speaker. Mihalis received his degree in physics from the Aristotle University of Thessaloniki and his PhD from Queen's University in Belfast. After he got his PhD, he worked as a research astronomer at the Center for Extreme Ultraviolet Astrophysics at the University of California, Berkeley, and then moved as a lecturer at Queen's University, Belfast. He was then promoted to a full professorship at Queen's University, Belfast in 2008. Mihalis is currently the head of astrophysics research at Queen's University, Belfast. Mihalis is a leading expert worldwide in both solar and stellar astrophysics. I would say that he's one of the very few people, experts worldwide, with strong contributions both to stellar and solar and stellar astrophysics. His work includes instrumentation, observations, and modeling of solar dynamic phenomena of all scales, all the way down from proper flares to small transient chromospheric phenomena, as well as stellar flares and activity in general, as well as solar-stellar connections. His output consists of more than 180 refereed publications, and he has supervised more than 16 PhD students to completion. Mihalis was the project scientist of the rapid oscillations in the solar atmosphere imager, a camera that takes the very high cadence images of the solar chromosphere, and this instrument is installed in the Dune Solar Telescope in New Mexico in the United States. More recently, Mihalis led the development of the detectors of the DKIST solar telescope, currently the largest ground solar telescope in the world. Mihalis was the chairman for UK Solar Physics and is currently the vice president of the European Association of Solar Telescope. His teaching involves courses on both mathematics and astrophysics, and also the supervision of laboratory work and final year dissertation projects. So the topic of Mihalis' talk is a very exciting talk. He will speak to us about ultra high resolution observations of the sun with the latest ground solar telescope. So the title of his talk is The Sun Under the Microscope. So without further delay, I'm giving the floor to Mihalis. Mihalis, please go ahead.
Well, thank you very much, Spiro, for the introduction. I am very happy, very pleased to deliver this colloquium to the Hellenic Astronomical Society. Today, I have very sort of fond memories of the first meeting of the Hellenic Astronomical Society, which took place in Athens in the early 1990s. I was a PhD student at that time. And Yannis Siradakis approached me and said, "Oh, we are forming the Hellenic Astronomical Society. Sign your name on this book and you will be a founding member." So I am actually a founding member of the society, and I follow what it does. And I'm very pleased that I did sign up at that time. Yes, the outline of my talk today, for some reason, okay, here we go, is I'm going to make a start by introducing the topics of magnetic activity. What do we mean? What do I mean when I talk about magnetic activity, and link those to the so-called solar-stellar connection? And for that first part, I will focus on large-scale activity. Then I will move into the sort of main part of my talk, which will be to talk about small-scale solar magnetism. and focus a little bit on structure and dynamics. What information can we get? And more specifically, how can we go from solar images to solar physics? I will spend a little bit of time to talk about the Daniel K. Inouye Solar Telescope, to which we have contributed the cameras that you have seen the first light images from. And I will also mention the European Solar Telescope. And finally, I will close again with the solar-stellar connection, and I will do it from another angle, from another point of view, from the point of view of how those high-resolution observations that I will be talking about can help us to understand and detect small Earth-size exo or extrasolar planets. Okay, so I will start off with the very popular image from the Swedish Solar Telescope, which shows sunspots. And sunspots are really one of the greatest manifestations of solar magnetism, large-scale solar magnetism. Dark areas on the solar surface, cool areas on the solar surface, and those sunspots are sort of associated with these bright regions, the so-called plage regions. We believe that sunspots exist in other stars, and the evidence for that, for the existence of solar-type spots on other stars, comes from the so-called effects of rotational modulation of the white light emission. So here we have an RSCVN binary. It's called Lambda Andromeda. It is a single line spectroscopic binary. So we only see, I'm sorry, I don't know why we went back there. We only see one. I'm sorry, but something wrong with my screen. We only see one of its components. And what we can see here on the top diagram is, the second diagram is the visual magnitude as a function of rotation phase from 0 to 1. That's one rotational period. And we can see that the object gets fainter and then brighter. And we believe that this is due to sunspot because at the same time, the object also gets cooler. When it gets fainter, it gets cooler. And when we look at the chromospheric emission, that is the H-alpha emission from the chromosphere, when the star gets fainter and cooler, we get more emission from the chromosphere. So that gives us an indication that we are looking at the spot plage scenario. And we can venture a little bit more, be a little bit more ambitious and look at more difficult lines like the helium-1, D3 line. There it's very difficult to see a clear rotational modulation. There's a lot of scatter points, but I think the picture that we are forming is that we can have in a phase 0.1, which is right about here. We have maximum number of sunspots, the largest number of sunspots on the surface. So the star is faint. And at the same time, we have a large amount of plages, which makes the chromospheric emission to be stronger. If we move to a different phase, 0.35, which is just about here, we can see that the star gets brighter because the spot has moved away, and we get less of the equivalent of plage regions. So that analogy seems to be ticking the box. Another example where we think that this magnetic activity that we see on the sun exists in other type stars is through activity cycles. So these are some observations that they were obtained from Mount Wilson, from the Mount Wilson calcium-2 line program, and focus effectively on the chromosphere. So the top diagram is the sun seen as a star. And again, we see the 11-year activity cycle. Well, it's about 10 years here, but it's actually an excellent set of data that show the activity cycle very, very well. So remember, the sun is a G2 star, so its B minus V index is 0.67. If we go to another G-type star, HD 81809, again, we see a very well-defined activity cycle, which is 8.2 years. If we go to later spectral types, we again see an activity cycle here, which is somewhat longer, more like 14 years. If we go to an even later spectral type, 0.96 is a B minus V, which is a K-type star, a well-defined spectral cycle of about seven years. And then there are some objects which kind of don't have very clear evidence of activity cycles, like this one here, which is an F-type star. It's pretty flat. Or another one here on the right-hand side, HD 187013, which is again an F-type star, and it has a kind of decline in its chromospheric emission, so it may be evidence for a longish activity cycle. So this set of data have been published in a sort of very well-cited paper that is led by Sally Banylunas and was based on observations that were acquired almost over a period of 30 years. However, I think I should point out that one of the very early observations for activity cycles came from the University of Thessaloniki, and it was reported by Lysimachos Mavridis and Stavros Avgoloupis, and that was on a dwarf M star. And these are observations in the visible that were taken at Stephanion Observatory. So what we see here is again the year on the horizontal axis, the B magnitude on the vertical axis, and we can see an activity cycle which is about 5 years. So the top diagram is the B magnitude, while the bottom diagram is the flare index, the frequency of flares and how big those flares are. And what is perhaps a little bit different, or perhaps a little bit confusing even in this diagram, is that the maximum number of flare activity seems to be happening about 1 year before the minimum light in the visible, before the maximum number of sunspots or star spots. So you can basically see that the horizontal axis on the bottom plot is shifted by about 1 year compared to the axis on the top plot. So again, I think this is one of the very first reports, and this paper has not really been cited as much as the Banylunas paper, but I thought that it was important that I should mention it. Another evidence for magnetic activity in other cool stars is simply the appearance of emission from the corona, and that's X-ray emission. So in this diagram, what you have on the horizontal axis is a parameter that we like to call the Rossby number, but to make things simpler, let's just say that it's rotational period. And the objects on the left here are fast rotating objects, while the objects on the right here are the slow rotating stars. On the vertical axis, we have the soft X-ray emission, the logarithm of the soft X-ray emission normalized to the bolometric luminosity of the object, because it's just a good way of normalizing the emission from the corona to the total mechanical energy that the star is emitting. So we can see that as the objects rotate faster, the proportion of soft X-rays increases relative to the bolometric luminosity until they reach a point where it no longer increases because they have saturated. The emission has saturated the emission from the corona. And then when we go to ultra-fast rotation rates, we actually begin to see a decrease in the soft X-ray emission, which is a somewhat puzzling effect, and we can discuss more about it later on. It's what some people call the effect of supersaturation, which is again the decline of the soft X-ray emission in the ultra-fast rotators. And just for context, I have 2 points for the sun here, one at solar minimum and one at solar maximum. Again, this is the quiescent X-ray emission. And you might say that the sun is a low activity star in this context. And the final aspect of magnetic activity and sort of global large scale properties of the sun and other objects, other cool stars, relates to flares. And this diagram does show us that the flares kind of seem to follow a power law. It includes both very small flares, what we might call micro flares, and some of the most energetic flare events that we see in other objects. So on the horizontal axis, we have the flare energy, and on the vertical axis, we have the flare frequency. So as you might expect, micro flares happen very, very frequently, but they have very small energies. And the largest flares do not happen very frequently, but they can have really devastating effects on their planets when they happen. What has been a great addition to flare studies has been observations from the Kepler mission. And the observation from the Kepler mission has been extremely helpful because Kepler has been able to capture many, many stars at the same time. So rather than observing a single object for very long periods, as we used to do in the 70s and in the 80s, with Kepler, we can achieve the same thing effectively, but by just observing a lot of objects in the same field of view, or not necessarily in the same field of view, but with the same satellite over a shorter period of time. So just to point a couple of features in this diagram, at solar maximum is the upper curve here with the three points here, which signifying the X-class flares, the M-class flares, the C-class flares, and then at solar minimum, we have the triangles below. And if one of the conclusions that came from the Shibayama paper that you may have seen is that a G-type star, a typical G-type dwarf, is going to produce a super flare, a flare much bigger than the Carrington event, once every 2,000 years. So those sort of flares, again, can have devastating effects for the planets that surround the host stars. Okay, so I'm now going to move on to the high resolution observations. And the facilities that the data that I'm going to be talking about basically come from these three facilities. The Swedish Solar Telescope, which is on the island of La Palma, the Dan Solar Telescope, which is in New Mexico, in the US, and the Gregor Telescope, which is on the island of Tenerife. All three of these facilities are around, I would say, 1 meter class telescopes. Well, the Dan Solar Telescope is 76 centimeter. The Gregor is, well, it's 1.5 meter. It's important to point out that the Swedish Solar Telescope that you see there on the left, even though it does not have the biggest aperture, it has probably produced some of the most spectacular solar imaging that we have seen, because it benefits from the fact that it's sitting at the edge of the caldera on the island of La Palma, and the laminar flow that is introduced by the caldera helps the telescope to achieve really outstanding scene conditions, near diffraction limited. Now, the issue, of course, with these telescopes is that they cannot provide us with full sun images. The trade-off between giving us a very high spatial resolution is that it will give us a small field of view. So this is an image of the sun with the Solar Dynamics Observatory. And I will be talking about very small scales. The field of view typically of one of these facilities is as small as the yellow box in the middle. So let's just focus there. And more specifically, I will be talking a little bit about granulation. Granulation, which is the dominant feature effectively of the quiet sun, and one of the most pronounced piece of evidence that convection happens. I will, for the benefit perhaps of the non-solar physicists, I will show this movie from Bob Stein, which shows a simulation of convection. Now, so if I play the movie, the blue colors show the hot material, which is rising and expanding, while the red colors show the cool material, which is sinking and contracts back into the convection zone. The depth of this simulation, I think, is about 40 megameters, 40,000 kilometers. And the granulation is, if I take now this box and I rotate it by 90 degrees, gives us this granulation images on the surface that we see. So the field of view here is 45 by 45,000 kilometers. And I'm going to focus a little bit more, zoom in a little bit more into an even smaller area, which is only 12,000 by 12,000 kilometers. I'm going to spend a little bit of time to talk about these tiny bright structures that you see, which are the so-called photospheric magnetic bright points. And you can see them everywhere, sitting in the intergranule lanes amongst the granule. And their typical characteristics is that they are very small. Their diameter can be as small as 150 kilometers, possibly even smaller. They are bright and they're highly dynamic. They are moving with the granular flow. They exist in the intergranular lanes. They exist in these dark areas between the granules, and their lifetimes is typically the lifetime of the granules, about 5 to 10 minutes, and then they disappear. To perhaps appreciate a little bit better what I'm going to talk about next, I want to emphasize that here we are in the high plasma beta regime. Okay, so the magnetic field moves with the fluid. Okay, so the hydrodynamics dominate the motion. Now, I'll spend a couple of slides to try and explain how those magnetic bright points, which have strong kilogauss fields, get formed. And I will use this simulation. On the left-hand side, you see a continuum intensity of the granules. And on the right-hand side, you're going to see the magnetic field that is going to start emerge into the intergranular lanes. So what's happening is in the convection zone, if I go back to the simulation here, the material rises and carries the magnetic field with it. And when it gets to the surface, the granules move the material horizontally. And as the material moves in the horizontal direction, the magnetic flux gets effectively advected into the intergranular lanes. And you're going to see it appearing on the right-hand side. So here we go. Now the magnetic flux gets advected into the intergranular lanes. And though that magnetic flux helps to form the strong magnetic field concentrations which have kilogauss field strengths. So on the right-hand side, what you see is effectively the Z component of the magnetic field. Maybe I will play it once more. There is a delay in having the magnetic flux appearing on the right-hand side of the movie, and there is a delay having the magnetic flux appearing because the simulations let the fluid settle first, and then there is an injection of magnetic flux at the bottom of that simulation box, and it takes some time for the flux to rise to the surface and gets advected in the intergranular lanes. So what you are going to see, and I'm going to point it out in a second, is that the regions that have strong vertical field on the right-hand side, now they begin to appear. So if I pick one of those regions, so if I pick that region there, the region that has strong field, nearly 2000 Gauss, also looks quite bright on the left-hand side. And the same applies to many other areas as well. So that region, again, a strong magnetic field has developed a bright area in the continuum image. Okay, so this schematic diagram perhaps can help explain what is happening. As the magnetic flux gets advected from here on the left, from the granules into the intergranular lanes, we have an increased magnetic pressure. And that magnetic pressure adds effectively to the existing gas pressure. But because the structure is in some kind of equilibrium, the gas pressure inside has to be reduced to balance out, so that the total pressure inside the flux tube needs to balance the pressure outside. But because the gas pressure inside the flux tube gets reduced, that means that the density is reduced. So the flux tube effectively becomes evacuated. So the density gets, there is a decrease in the density, and that decrease in the density happens with an increased velocity, downward velocity. So the material gets sucked down effectively that flux tube. And because the density is decreased, that means that the optical depth, which depends on the density, is also going to be decreased. So if you pick an optical depth of 1 or an optical depth of 2/3, if you look outside the flux tube, you are going to see a higher geometrical height than the geometrical height that you are going to see inside the flux tube. So inside the flux tube, you are basically, you can see material deeper into the convection zone, and because deeper into the photosphere, and because it's deeper into the photosphere, the temperature is higher, and therefore we see hotter regions. So we see hotter regions for the same optical depth. This slide just shows you that observations and simulations seem to agree pretty well. So when it comes to granulation, we can say with some confidence that the models, the radiative magnetohydrodynamic models, seem to be getting right. There is very good agreement between the two. We can see the granules, we can see the bright points, and that's encouraging. Many years ago, going back to 2010, I had a PhD student, and I asked him at that time, well, one of my PhD students, I asked him at that time to try and see whether we are resolving most of these small scale structures. Do we see most of these magnetic bright points? So he effectively went away and studied more than 60,000 of them, and try to determine their size, try to determine their dimensions, and then came along and plotted this magnetic bright point size distribution, which is a normalized distribution. So on the horizontal axis, you have the area, the size, if you like, of these magnetic bright points. And on the vertical axis, you have their normalized number. Now, when we see distributions of this type, and we see a rise in the number, we see many of the smaller bright points. You might expect that. And then we have this other drop. Then we start wondering whether we're reaching our detection limit here. And this drop in the number is not real. It's an artifact of our detection capability. So that's one thing I would like to come back to. On the smaller, on the inlet here, I have a zoom in of this distribution, but I'm zooming in only at the peak. So I'm zooming in between 0 and 120,000 kilometers square. So it's only this part. Okay, so what else do I have here? I have 3 different colors. The red is the observation, is what Philip Crockett did. And then the blue and green are the same exactly the same type of work, but using the MURAM, the radiative magnetohydrodynamic simulation cubes, to do exactly the same thing, to measure the size of these very small magnetic bright points and determine their distribution. Now, it's important to highlight that the diffraction limit of the telescope is this vertical line here on the left. It's about 10,000 kilometers square. So the peak of our distribution is well clear of that detection limit. So we seem to be seeing most of these very small scale structures. And again, the agreement with the simulations is very good. And I would argue that the agreement with the simulations is very good, no matter what the magnetic field that we inject at the bottom of the convection zone is. Even if it's 200 Gauss, even if it's 100 Gauss, even if it's 50 Gauss, that magnetic field will still get advected by the granules and form kilogauss concentrations, which are going to have similar sizes. Okay, so this is just a summary of what I have just told you, so I'm going to skip that and go to the next slide. Okay, so now I'm going to move into a little bit of the physical parameters that we can get from these structures. And this is the point again where we turn kind of observations to physics. Now, it's important, I always remind my students that when we study light gives us intensity, photons, we get the wavelength of light, frequency of those photons, but there is a third parameter that we often ignore, and that is polarization. And polarization, the properties of polarization are reflected in the Stokes profiles, the Stokes parameters. And the Stokes parameters are these four parameters here, which is, well, the first one is the intensity, just plain intensity, no polarization, the intensity of these two spectral lines in this case here. And then we have the amount of circular polarization, which is given by the so-called Stokes V, the Stokes V profiles. And then we also have the amount of linear polarization, which is given by Stokes Q and Stokes U. And to convert these Stokes profiles that we observe into the physical properties, and by physical properties, I mean the field strength, the inclination angle with respect to our line of sight, as well as the thermodynamic properties, the temperature, the density of the plasma, the velocity of the plasma, we need to use inversion algorithms. And the inversion algorithms effectively compare the observations, and the observations is what we call here a reconstructed line profile. So it's the dashed line with an attempt to fit those line profiles with different models. And those models will have to make assumptions, such as whether we are in local thermodynamic equilibrium or whether we are in non-local thermodynamic equilibrium, what type of model atmosphere we are employing. And that, of course, depends on the type of diagnostic that we are dealing with. If we are deep in the photosphere, we can talk about lines forming in LTE. If we are in the chromosphere, the lines will be in non-local thermodynamic equilibrium. Yes, so attempting to get the best possible fit to the observations, and we get a set of parameters that tell us the properties of the atmosphere. You can, there are two different types of inversions here. The scheme 1 means, for example, that you only have one magnetic component. Scheme 2, that you have two magnetic components. Whether you have a constant magnetic field within your resolution element, or whether you have gradients within that magnetic field. So all those uncertainties, or those variables that we can choose, and we have to be aware of those, because those, of course, have some limitations on the output that we receive. Okay, so this is a structure. This is a figure that explains or helps to visualize what's happening in a magnetic bright point. On the top, we have the intensity, and this is over a lifetime of about 600 seconds, just about 10 minutes, just over 600 seconds. And on the top, we have intensity, and you can see that at a time of around 400 seconds, we have maximum intensity. Okay, the bright point becomes brightest in that intergranular lane. At the same time, the magnetic field, which is the blue line, the line of sight magnetic field, reaches a maximum. Okay, reaches a maximum at almost 2,500 Gauss. At almost the same time, the line of sight velocity, which is the red line here, reaches maximum downflow, 3 kilometers per second. So as I said earlier on, when the tube becomes evacuated, the plasma flows deeper into the photosphere, and the magnetic field becomes stronger at that time, and we see this very good correspondence between the two. And the inversions can also give us the temperature as well as the gas pressure for different optical depths. So one point that I would like to mention here is that the magnetic field of this bright point is going from about 400 Gauss, which is just here on the left, kind of remains pretty much stable for about 350 seconds, and then suddenly it jumps very quickly to 2,500 Gauss. So this amplification process happens extremely quickly. And then the bright point does not live for very long at that very high magnetic field. It seems to come back down to 400 Gauss fairly quickly, literally in a minute, in about 60 seconds. So why does that amplification happen? Well, the amplification can happen because of different scenario, and we see all that scenario, both the observations and the simulations. We can have merger of bright points, so small bright points which come together to form bigger ones, so you have more magnetic flux in a small area. We can have increased vorticity, which seems to amplify the field also. As I said earlier on, we are in the high plasma beta regime, so the granules, which are kind of not so magnetic, compress the bright points in the intergranular lanes, and that again amplifies the field. And the process of convective collapse, which is effectively the evacuation of the flux tube, also helps to amplify the field. As I mentioned, I did mention vorticity, so I want to show you this very nice example of what I mean with vorticity. This image is a little bit, it's not very clear, but it's actually at extremely high resolution, so that's why it's not very clear. The bar that you see here on the bottom left-hand side is 1,000 kilometers. So effectively, this is a granule. Okay, so as I play this movie, you are going to see some material which is going to come in along this intergranular lane, and they're going to go into a circular pattern, and you're going to see a brightening developing here, which again is one of the processes that seems to amplify the field and create a bright point. So you can see it there. So the bright point gets brighter. I'll play into once more. You can see the material coming in and entering. So this is what we mean when we talk about vortex flows. I should emphasize here, I should point out here that there is a lot of work with vortex flows that has been done by the National Observatory in Athens. Kostas Georgiou, Georgia, Tsouropoula, and Yannis Kondoyannis have published a series of papers where they explore this topic and all the other sort of wonderful effects we see associated with vorticity, such as waves and oscillations. So you may want to look at it. I think I'm going to skip that slide and come to the topic of magnetic flux cancellations. So magnetic flux cancellations, or well, photospheric reconnection, as some like to call it, we also have a lot of evidence for that, and we can study it in the smallest scales. And I would like to mention the paper that Manoli Orwood published back in 2002, which is a sort of, I think, an influential piece of work because it does explain a number of scenarios that help to understand why these magnetic flux cancellations happen in the photosphere. And there are the three basic scenarios. We can have converging flows of opposite polarity, and those converging flows happen in the granules. The granules can push those bright points, which can be of opposite polarity, together, and we can have the effects of they can cancel out and release their magnetic energy. We can have another scenario where we have the moving dipolar flows, magnetic dipolar flows again, which can change the topology of the field and result to these cancellations. And the third scenario here is where we can have the flow in the vicinity of the sunspot, which the flow in the vicinity of the sunspot can be horizontal, and that horizontal flow interacts with the vertical flow from the vicinity, the quiet sun, and that again creates those magnetic flux cancellations, which were first reported by Ellerman 100 years ago and also known as Ellerman bombs. So I just want to show you a movie that demonstrates this last scenario. We have the sunspot here, and we have the flow coming from the penumbra, which is horizontal. And that horizontal flow, which is this schematic diagram here, seems to be interacting with the vertical flow, which is in the vicinity of the penumbra, and create some of these magnetic flux cancellations. This is a study that was done by one of my PhD students, Aaron Reed, some time ago, which was to study those cancellations in some more detail. Again, we're looking at some extremely high resolution images here. The spatial resolution is down to 150 kilometers. On the left-hand side, we have a movie of H-alpha, but not the core of H-alpha. This is the wing of H-alpha, which is formed in the photosphere. So it's core minus 1.2 angstroms. So it's out in the line wing. And you see this brightening here. On the right-hand part of the diagram, you see the Stokes V profile, which is effectively, not effectively, it is the line of sight component of the magnetic field. So you can see two opposite polarities. The dark and the white are two opposite polarities. So as I will play the movie, you will see that the flows are bringing the opposite polarities close together. And then as the black and white polarities begin to interact, the flux cancels out, and we have the release of radiative energy on the left-hand side that you can see it in the H-alpha image. And we don't have just radiative energy. You can see all these jets emerging. So I think this is a nice example which demonstrates how, again, the dissipation, the cancellation of the magnetic flux turns into radiative energy, and not just radiative energy, kinetic energy as well. And I will let the movie finish, because towards the end, again, the two opposite polarities will begin to diminish, and at the same time, the brightness of the image on the left will also die out. Okay, I will go into this slide, which has to do with the corona, and I'm going to try and explain how these observations, the ground-based observations, can also help us gain a lot of insight from the corona that is usually only available to us from spacecrafts. So again, to make the contrast, this is the low plasma beta. Okay, so the fluid now moves with the magnetic field. The magnetic field dictates the motion. And the building block of the corona is supposed to be these magnetic loops that we see everywhere on all size and scales. And this particular movie here, if you want to assign a characteristic temperature to it, it's a temperature of about 1 million degrees. And the spatial resolution that you would get from SDO, from the Solar Dynamics Observatory, is about 1,000 kilometers. I don't see the next image appearing. Here it is. Okay, so this is a comparison of a zoom in area of those magnetic loops. So on the top two panels, you have loops observed by SDO at the limb. Now again, they don't look very pretty here because I have zoomed in and the resolution of SDO is only 1,000 kilometers. Where at the bottom two panels, I have the same field of view, the same structures observed from the ground with the CHROMIS instrument in H beta. The H beta is the 4:2 transition in hydrogen, and they have been observed with the Swedish Solar Telescope. Now, I might argue that we are looking at the same structures here. Okay, so the same structures are seen both in chromospheric and coronal lines. Just to highlight that in the SDO image, you can see this very bright area at the loop top, and you can see the same bright area at higher resolution in H beta from the Swedish Solar Telescope. You can see this dark area, which is some absorbing material in the H beta core, and you can kind of see very similar area in iron 9, iron 10, as well on helium-2. So we are looking at the same structures. So we decided to try and benefit from the fact that the ground-based observations allow us to determine the magnetic field, to get the magnetic field of those coronal loops, which are multithermal, right? They also emit in chromospheric temperatures. So on the top left-hand side image, I have the velocity field. So on the right-hand side of the loop, we have material which is flowing towards us at about 30 kilometers per second. On the left-hand side, material which is flowing away from us at similar speeds. The intensity is the image on the top right-hand corner, and you can see this extremely high resolution, the fine threads that the loop is made of. And now we come to the measurements of the magnetic field. Now, this image at the bottom left-hand corner, image C, is not as pretty, but you have to appreciate that what we see here is a line of sight component of the magnetic field in these coronal loops at very high spatial resolution. And we have divided this image into three parts. Part 3, which is the one closest to the limb, and that applies to the bottom right diagram here, which gives us the occurrence of how frequently this line of sight magnetic field occur in the bottom 3, then 2 and 1. So what you can see here is that we can have the magnetic field can reach values as high as 350 Gauss at 25 megameters, 25,000 kilometers above the limb. So I think this is by some seen as a surprising result, because the magnetic field in the corona is usually thought to be quite low, the order of a few Gauss, typically tens of Gauss. But we are seeing magnetic field in loops which are hundreds of Gauss. And the other interesting point is that these magnetic fields, these loops, seem to be sustained for a long period of time, 30 minutes or longer. They actually lived longer than our observations, but our observations were not very long. They were only about an hour. Okay, so I will now move on to DKIST, which is the third part of my talk, and I'm really not going to take much more time because Zoom fatigue will kick in shortly. So DKIST is a 4-meter telescope for solar physics, and to put it in context, we move from 1-meter class facilities to 4-meter class facilities to nighttime astronomers. This is like going from the 4-meter to the 10-meter. or the 8-meter class facilities. DKIST is on Haleakala in Hawaii, and it will basically cover the spectral ranges from the near UV up to 5 microns to the infrared. Spatial resolution 20 kilometers on the sun's solar surface. And in terms of science objectives, it will give you very high resolution imaging, 20 kilometers. It can provide imaging spectroscopy, spectropolarimetry, as well as coronal magnetometry. It has no coulter, so it can be used also as a coronagraph to simulate eclipses. If I'm going to cut a slice through DKIST, this is what it would look like, a section through the telescope, the observatory. So the top of the telescope extends to about 42 meters above the ground. The telescope is sitting here at the top, and then the light comes all the way down to this level, which is the CUDE level, where all the instruments sit. So the CUDE level now, I have another image of it on the right-hand side. The CUDE floor, the CUDE lab, as it's also known, is about 16 meters across. So the light comes from above, and then it gets distributed to the various instruments. So we have the visible spectropolarimeter, on the top here, the visible broadband imager, the red channel and the blue channel, the diffraction limited near infrared spectropolarimeter, and the cryogenic near infrared spectropolarimeter. To give you an idea of dimensions, again, the VTF here is about 2 meters high. And you can see at the CUDE level, the whole of the CUDE floor rotates to follow the sun, and the computers, the servers are hanging below the floor, and they rotate with it. The contribution, or our contribution to DKIST, was to provide the cameras that equipped all the instruments in the visible. And this was a custom design sensor and a custom design camera. When we started on this work back in 2013, developing it, there was no other camera in the market that could fill those requirements. So the camera that we designed and manufactured is a 4x4K camera, CMOS, and it can acquire up to 60 images per second, 60 frames per second. It's one of the largest CMOS sensors that exist. It's almost 8 centimeters diagonal. And the funding for developing this camera was provided by our funding agency and the universities that you see here at the bottom, and a group of UK universities. We did this together with Andor Technology, which is a spin-off company from Queens University. It was set up by a group of physicists many years ago. And we sort of maintain a good relationship with them. One of the reasons is that they can work with us to do custom-made solutions for what we want to, for our science. And the second is that they employ many of our graduates because it was built up by physicists and it's run by physicists. They kind of appreciate the skill that a physicist acquires. It's right on the peace line. If you know the Belfast history, it's right on the sort of interface on the peace wall, as some people often call. The name of this camera is called it's Balor, and it was named Balor after the mythical single-eye giant from Irish mythology. I did tell them that the Irish mythology stole its ideas from the Greek mythology, because in Greece we call them cyclops. But I think I lost that battle. The name Balor won. And it is possible that you might have one of the Andor cameras in your telescope, in your observatories, because they have been selling quite a lot to astronomy. And this is the first light DKIST image that was obtained with the telescope and with our camera. It made the front page of New York Times. It was classified as one of the best science images for 2020 by Nature. And I guess when you look at this image, you say, what is new in this image? There is probably not very much new. It's granulation. We know about granulation. We know about the bright points. We see them all over the place, but we never saw them at this level of detail. And the science will have to be done. The analysis of the data will have to be carried out for the new science to emerge. But it is a science verification image, so it does show that the telescope does work to specification, and it can achieve its diffraction limited resolution. I think I'm going to mention quickly the European facility, which is designed, it's planned, is a European Solar Telescope, which is a 4-meter on-axis telescope. The plans are to build this facility on the island of La Palma. It's one of the 6 facilities that has been approved in the European the ESFRI roadmap, research infrastructures, European Social Fund, I think, research infrastructures roadmap, and it's going to be located where the Dutch Open Telescope currently is. At least that is the plan. First light is expected in around 2028, and there are 27 partners involved in the design phase from 14 different European countries, including Greece. So there is some way to go because the funding for EST is not there yet, but there is certainly hope that this facility will also materialize. I think I want to mention that the European Solar Telescope has recently launched an outreach contest, a school contest for secondary school pupils, 14 to 16-year-olds from anywhere in Europe. And the aim is to design an infographics where the sun is a protagonist. And the idea is to pick basically a topic from solar physics and try to explain it concisely and in a way that will appear to a non-scientific audience. The top 2 designs will win a trip to the Canary Islands, and they will also have VIP tours of the telescopes and the labs, and that will apply both to a teacher and 4 pupils from each team. The third team will win an H-alpha telescope for the school, and all the entries are going to be acknowledged and including the so-called solarpedia. So, if you have any connections with any schools that might be interested, please pass this information on. Okay, I'm coming to the end of my talk, and I'm now going to briefly mention how we think that the high spatial resolution observations that I've just talked to you about can help us understand cool stars, and not just understand cool stars, but also detect the Earth-sized exoplanets that are surrounding many of them. Now, we know that the detection of exoplanets relies heavily on the radio velocity signal that is induced on the host star by the exoplanet. So this is an example here. We have the exoplanet circling around the host star and inducing a small wobble on the host star, and that wobble can be seen is in various, can potentially be detected in various photospheric lines. However, an Earth-sized planet will typically induce a radio velocity signal of a few centimeters per second on a late type star. The current spectrographs that are currently being designed, they are designed to reach precision of a few tenths of centimeters per second, and there is nothing really, there is no big technological barrier that will stop the few centimeters per second precision from a spectrograph perspective, as far as I understand. However, there is a problem, and the problem comes from the signal that from the astrophysical noise, from the solar noise, from the radio velocity signal that comes from the granulation of the sun itself. And one way to describe the problem is with this figure, which is it was given to me courtesy of the HARPS North Consortium. And in this figure, you basically have on the horizontal axis days, mean Julian date. On the vertical axis, we have the radio velocity signal, radio velocity jitter in meters per second, okay? So the signal that the Earth induces on our sun is the red line here. It's tiny, okay? It's a few centimeters per second. You cannot see it very well in this scale, but there is a few centimeters per second signal here. And unfortunately, that signal is masked by the radio velocity signal that comes from the sun itself. It comes from the sun as a star, from observations of the sun as a star. And granulation plays a very important factor into that. This is my final slide to try and demonstrate what I mean by granulation playing an important factor and how we can disentangle it. This is a study that we tried we started a few years ago. And the idea was that if we create models of radiative magnetoconvection with MURAM, which seem to be capturing the physics of the sun very well, and then take those models, take those small field of views and tile the sphere. So create effectively a sun as a star model by creating those tiles and fill the object. Each one of these structures on the solar surface, the granule, the intergranular lanes, the magnetic bright points, have their own distinct line profile. So the granules have this green line profile here. The granules are material which is coming towards you, so it's blue shifted at about half a kilometer per second. And the intergranular lanes, which is material sinks, so it's material which is going away from you, sinks faster, so it sinks at velocities as high as 3 kilometers per second. But that material, the intergranular lanes, is described by those the purple line and also by the red and blue line, depending on whether you have bright points in them or you don't have bright points, the magnetic bright points. And the magnetic bright points are those kilogauss fields. So you can see in these line profiles even the splitting caused by the Zeeman effect. So the idea was that if we tile the object and then have a sun as a star spectral line, are the effects of granulation, material coming towards you, the effects of intergranular lanes, material coming away from you, going to cancel out? And the result is that unfortunately they do not cancel out. You are still ending up with a residual noise of a few meters per second, which is effectively which is all the scattered points that you saw in the previous slide. So all these scattered points are basically the fact that the granulation, the effects of granulation in the granular lanes do not cancel out completely on a sun as a star model. But there is possibly a scenario where, if you have a certain star that has the right coverage of granules, the right coverage of intergranular lanes, you might be able to minimize the effects of granulation. You might be able to push the few centimeters per second down to the centimeter per second level. But in order to do that, we must be able to understand clearly the line profiles that emerge from these very small high resolution images and the impact they have on the star as a whole. I think I'm going to stop here, and thank you again for listening. I'm sorry that this took a lot longer than anticipated, but I'm happy to answer any questions that you might have. I don't know whether I should perhaps cancel the presentation.
Thank you very much, Mihalis, for this exciting journey from the stars to the smallest features we can currently observe in the sun and back to the stars. So time now for discussion, questions. So please raise your hand so that you can speak with Mihalis. Angelos first.
Mihalis, πολύ καλή παρουσίαση, πολύ ενδιαφέρουσα.
Maybe in English.
Με ακούτε?
Yes, but
yes, we can hear you, Angela.
Πολύ ενδιαφέρουσα η ομιλία. Very interesting presentation indeed. I would like to get some of the slides from you later. I have a couple of questions, but I'll ask only one now relating to the H-beta results that you showed with the loops in the corona. I think my understanding is that these measurements of the magnetic field and all that stuff rely on a lot of assumptions, you know, on whether emission is optically thin or the line of sight is clean and all that. So what is your own sense for the accuracy of those measurements?
Okay, I think that is a very important point. I did touch a little bit on the, let me see, why I can't go back. Do I still have control of the screen? I do, yes, sorry. I think I did touch a little bit on the aspect of the accuracy of the measurements when it comes to inversions. And I because I did say that the model atmosphere that are applied do have some limitations. The good thing, though, Angela, about the observations of the H-beta that I showed you, and this is the movie. Sorry, it's not the movie. The images of the H-beta here. The magnetic field measurements here were made with the calcium-2 infrared triplet line, which is also a chromospheric line. But the good thing about the method is that it is based on the so-called weak field approximation, which means there is no inversions involved. And the weak field approximation means that, okay, there is a strong field approximation and the weak field approximation. The strong field approximation applies when you have a very strong field so that the Zeeman broadening is bigger than your Doppler width. And that's what's happening in a sunspot where you have a few kilogauss, even in a magnetic bright point. The weak field approximation applies when the Zeeman splitting is smaller than your Doppler width. And in this case, you don't have to apply inversions. Now, you raise the issue about the line of sight effects. Yes, if we try to do this study on the disk, we clearly have a problem with line of sight effects, especially if we want to start to use coronal lines to do the study. But we have to remember that chromospheric emission is optically thick. So if we are going to use a chromospheric line and we observe, for example, the line core, that is our tau equal to 1 layer. We are not integrating through it. We're just looking at the surface of the medium. So these lines, this line, the calcium-2 infrared triplet, at the limb is indeed optically thick. We cannot see through the loop, but we can see the surface of the loop. So I would argue that the measurements in this particular case are kind of robust, and they are not limited by line of sight effects. Because if we had more calcium-2 material in between ourselves and the loop, that would have been optically thick, and we wouldn't be able to see the loop. Did I make that point clear?
Yeah. Okay. Yeah, we can discuss it also a little bit more in detail later. But yes, thank you.
Thank you. Other questions? Kostas, Georgiou?
Thanks, Mihalis, for this very interesting talk. I just have a comment, and I would like to ask your opinion about that. You showed all these, magnetic bright points, but there is also, simulations, again, by Sergei Selyag, Moll, with Muram simulations, and also by Kobold, Freitag, and Calvo lately, that show that you can actually have a similar effect when you have an intergranular vortex flow. So when you're having a rotating funnel, you can actually evacuate the flux tube exactly the same way that you evacuate it when you have a magnetic field. And then you create the so-called non-magnetic bright points, okay? So far, of course, you know, we have been observing with lines that actually are strongly affected by the magnetic field, and that's why we mostly associate them with magnetic fields, like you know, calcium lines or iron lines in the photosphere and so on. But do you think that with DKIST we will have a possibility basically to disentangle between the two effects, whether actually, you know, what we see as an intensity brightening is actually because of the magnetic field role, or possibly also a hydrodynamic effect caused by rotating flows there?
Costa, I don't think that we necessarily need DKIST to disentangle that. I'm pretty sure that non-magnetic bright points exist. Okay, I mean, if you have a localized brightening like the ones here on the screen, can happen if you have an increase in density. So if you have an increase in density, the line is going to get brighter. If you're in the optically thin regime, it will go as the square of the density. If you're in the optically thick regime, it will not go as the square of the density, but again, an increased density will increase the brightness. I think what can be done relatively easily, in my opinion, is to have like a panel like panels like this, and next to it you can have a panel which will show the magnetograms. So you will probably find areas, bright areas like this, which are magnetic bright points, and some of those areas will be associated with kilogauss fields. Other areas will not be associated with kilogauss fields, and those you might call those the non-magnetic bright points. Does that answer your question?
Well, partly, because you know, I mean, you can actually have both effects, you know, acting. So actually, you can have, for example, a rotating intergranular vortex flow, and at the same time you have, you know, a colloquial magnetic field line, but you don't actually know what the exact effect of the magnetic field and the exact effect of the rotating funnel, the hydrodynamic effect of the magnetic funnel is actually on the production of this intensity enhancement. So yeah, the question still remains, you know, for me, you know, which of the two mechanisms actually prevails in this case?
So, I mean, do you think it's a matter of resolution? Because I'm just trying to understand how a factor
I think it is a matter of resolution. I think it is a matter of resolution. Well, I'm a little bit skeptical though how better the resolution is going to be compared, you know, to present instrumentation like the SST. You know, how far down to the diffraction limit of the telescope we can go. So that's why I'm asking you as a DKIST specialist to tell me, you know, whether we can actually achieve this kind of resolution to start talking about the effect of these two different factors.
Well, I think when it comes to imaging, the resolution can be achieved. So you can, you know, we saw it from the titanium oxide movies that DKIST can achieve the diffraction limited resolution on imaging. Now, when it comes to spectropolarimetry, it's a different issue because for spectropolarimetry, there is an appreciation that trade-offs have to be made. So if you tell me I want to resolve a 20-kilometer structure with DKIST, yes. If that structure exists, you will be able to resolve it, or you will be able to resolve fine structure at that scale, perhaps. But whether you will be able to do the full spectropolarimetry at 20-kilometer resolution is a different issue because you are starting for photons. So I think the setup, or not the setup, the understanding is that spectropolarimetric observations in the first instance at least, are going to be done at twice the diffraction limit. So I think you could say with some confidence that this Port-DL NIRSP will be able to resolve the magnetic field at 50 kilometer resolution, but I don't think it can be done at 20 kilometer resolution.
Okay, thanks.
That trade-off always has to happen. It does happen with every mission, I guess.
True. Thanks.
Other questions, comments to Mihalis?
I have more if nobody else wants to go.
Okay, go ahead, please.
Okay, now switching to the exoplanet. Exoplanets stuff that you were talking about, using the sun as kind of like a proving ground for understanding stellar observations. I was not clear on what you were saying in the end, that how do we actually, you're saying that we will use the sun to understand the effect of the granular velocities on the signal and be able to somehow remove it. That's what you were, that was your aim.
Okay, let's start off with this image, which I don't know. I hope this is clear. If it's not clear, I can explain it again. But the point is that this is the signal, the radio velocity signal, the wobble that the Earth causes on our sun. Okay, and if we observe the sun as a star,
I see.
Granulation on the sun produces a much bigger radio velocity signal than the Earth on the sun.
Okay.
Sorry?
Do we see this type of signatures in other stars? This sort of large scale sort of variability?
This is not, this is variability that happens in small scales and does not average out. I think that's what I tried to show in my next slide. Let's see if I can go to my next slide. So what we try to do is say, right, the material rises in the granules at half a kilometer per second. It sinks in the intergranular lanes much faster. It's a smaller area, so it has to sink faster. If we average, do we get a zero radio velocity signal from the intergranular lanes and the granules? And the answer is we don't. If we treat the sun as a star, we get a residual signal of a few meters per second. And that residual signal of a few meters per second caused by granulation is what gives us this scatter that we see.
Okay. So we got the stars. Do you see this type of behavior, or we're not there yet in accuracy?
Well, in stars, we have not been able to detect Earth-side exoplanets yet. We have been able to detect large exoplanets, Jupiter or super Jupiters, because they induce a much bigger radio velocity, which overcomes this signal that the star itself produces. You know, the point, I guess, is that you have this single spectral line, or this group of spectral lines that come from the sun or from the star, and those spectral lines, and from these spectral lines, you try to disentangle the exoplanet signal. But on top of that, you also have the granulation signal, because it's a stellar, it's a stellar or the solar spectral line. So what I'm trying to say is, if we come up with some form of parameterization where we understand the line profiles that come from these small scale structures as much as possible, and we kind of seem to be understanding them to some degree. So we have 4 different line profiles here: the green for the granules, the purple for the magnetic bright points, for the non-magnetic, lanes, dark lanes, the red for the magnetic bright points. And then we try an amalgamation, if you like, of these profiles, taking into account different percentage
Yes.
on the solar surface, we may be able to come up with a scheme where this scatter, these blue points, are compressed.
Mm-hmm.
And then we can try and find the star that may obey that scheme, because that star which will have the compressed signal will give us the best option of finding an Earth size, of detecting an Earth size exoplanet around it.
Mm-hmm. Mm-hmm. I got you.
I hope that was a little bit more clear, maybe.
Yeah, I thought that we have this data already, and so I was wondering why we cannot just model, you know, the observed stellar jitter with different what you just said, you know, with different parameterizations of the components of the sun. But I guess we need more data from the sun. You think?
Well, there is a big fraction of the exoplanet community has shifted now to the sun, and they are using a lot of data from SDO and from very small solar telescopes that they observe the sun as a star, but they are connected to the same spectrographs that they observe exoplanets with, because they want to replicate exactly the same conditions. So there is a big fraction of the exoplanet community, and because it's also the effect of spots, right? The spots are also going to induce asymmetries on the line profiles. They don't worry too much about the spots because the spots are so big that the asymmetries are quite distinct, and they can be taken out from a line profile. But they worry mostly about the blue shift and the red shift that the plage regions, the granules, and the granular layers are producing. And there is a lot of effort to try and understand that.
Okay. Thank you.
Any other question? I think Kostas has just left his hand up. Costa, do you have another question?
No.
Oh, okay.
No. Sorry.
Okay. Oh, no problem. No problem.
It's okay.
Okay. So,
can I have another question, please? But I don't know how to raise your hand here.
Okay, Kosti, go ahead.
Turn your camera on. Do this.
You can put the camera,
Okay.
yeah.
Please. Can we go back a little to these loops that Angelos mentioned also? So the fact is that you have high magnetic fields of the loop to high altitudes, and have you thought if could this perhaps explain why you don't have the cross section of the loops rising with the altitude? So you mean you find this was my question more or less. Have you tried to model this data to try to find what could be the magnetic field along the axis of these loops?
The magnetic field measurements, Costa, is as good as the bottom left-hand side image that you can see here. So the magnetic field is not, the magnetic field map, if you like, is not as spectacular as the imaging data. But you know, you perhaps one has to appreciate that those measurements are not very they're very difficult. They are not easy to get. In terms of the cross section of the loop, I think if you look at the top right-hand side image, which is the continuum intensity, which is the calcium 2 line intensity with respect to the continuum, normalized to the continuum, you can see that the loops are just a bunch of threads. Now, one might say, right, I'm going to put a slice across here and determine how many threads make up what seems to be a single monolithic structure, perhaps in the SDO image. But again, looking at the high resolution image on the top right-hand corner here, I would say that those threads are down to, okay, each tick mark is 1,000 kilometers. I would say there are less than 500 kilometers. They are very small. There are a couple hundred kilometers.
Mm-hmm. Yes. So these measurements are along the line of sight. So there is a fraction of the axial magnetic field which is represented here. So perhaps you could combine with the Doppler shifts that you have in the upper left image to see what percentage of the axial magnetic field you measure? Can you do such a thing?
Yes, I guess one can try and speculate what the total, if you like, magnetic field is by using by using the velocity vectors, if you like, because one can determine the line of sight velocity by looking at how the line moves, but also can determine the plane of sky velocity as the move.
Proper motions.
And that's something, yes, the proper motion effectively, and that is something worth doing. But for this piece of work, our main objective was really to try and show that magnetic fields can be extremely strong, and in the radio observations actually do show that magnetic fields are strong in the corona, but not at this resolution. Radio observations have a lower spatial resolution because lambda is very far into the longer wavelengths.
Well, on
Okay,
that, since you started the radio, going down the radio rabbit hole here, yes, indeed, I have found in a paper back in 2005, I noticed 2,000 Gauss fields at coronal temperatures, and I interpret those as being very low in the atmosphere, implying a very shallow gradient for the magnetic field, which makes more sense to me than say having a magnetic field at high heights. Now, in this case, though, I'm looking at the paper. This is the September 10, 2017 CME and flare, and to me that's not unusual to have a couple of hundred Gauss. From what I see on the lower left figure, you have a couple of hundred Gauss at 20,000 kilometers. So given that this is a post-eruptive, what you're looking here is the post-eruptive current sheet and flows coming down on it. I'm not surprised that much, but it makes me even more suspicious of the interpretation, though, because in that case we're quite far away from LTE. But you have to try somehow and get the field.
But Angela, there is no assumption of LTE or non-LTE here. The quick field approximation is just a straightforward equation.
Doppler shifts are coming in. The Doppler shifts and all that stuff. This is a disturbed plasma situation.
But I mean, the Doppler shifts again from observations. You see your spectral line, right? You can, and you don't see just the spectral line. You also have the Stokes V profile, so you can see if the Stokes V profile has been shifted. So yes, I do appreciate that this is the post-flare loops from the X 8.2 or 8.3 flare, but I won't classify them as flare loops as such because they seem to be sustainable for a long period. It's not like that and it's, we are not making assumption of hydrostatic equilibrium to get a magnetic field. So I stand by the fact that those measurements are kind of robust. Let's put it that way. Yes, the radio observations, as you said, and I also mentioned it, show that there are strong magnetic fields in the corona, but here we see them at very high spatial resolution.
This is great stuff. Absolutely, I'm not. Take me wrong. This is great stuff. I'm just saying that this is a particularly intense sort of situation. So the magnetic fields may come up in the corona. This has other implications, of course, for particle acceleration and whatnot. So it is important to know that you can get those Gauss, those numbers high up for sure. Yes.
I mean, you might say, well, you are looking at the chromospheric line. You are looking at a 10,000 degree line. Do you really call it the corona? Well, I might say then that, well, how do you define the corona? Do you define it in terms of temperature or in terms of height? Because these lines, these sort of chromospheric loops, if you like, and coronal rain, which is another phenomenon which is seen in chromospheric lines, extend very high above the limb. So
it is important for the CME and sort of all this association with how much magnetic field basically is involved in disruptive events. What you say is very important. It doesn't really matter the temperature of the material, but what is the magnetic field that eventually participates and is ejected. And the temperature is a fleeting thing, right? Things are cool in one picture and they're extremely hot in the next. So
exactly, and the same applies where you see different iron lines. You know, the iron 9s and iron 10 become diminished because the material gets ionized to iron 14, 15, 20. So because there is only a fixed amount of iron there.
Mm-hmm. Exactly, that's right.
Other questions, Mihaly? I got a very short one. Again, about this very interesting observation. So do you have any plans to repeat those observations in other targets?
Well, it's, you know, it's the point about capturing limb loops is a little bit of a hit and miss, I have to say. And it's also because you have to be lucky with atmospheric scene. You know, those from the audience that they have used ground-based observations know that the good scene conditions, the stable scene, it does not come very often, and when it does come, it does not stay for very long. There is some follow-up observations, Spiro, that apply exactly the same technique on coronal rain, which is which is basically chromospheric material, which has evaporated and then comes back down to the chromosphere. So if you want to look, there's a paper by Dato Kuric, which I'm not a co-author in that one, but you may want to search it into ADS. It was published in 2020 or 2021. I don't think he's the first author, but he's one of the co-authors, where they employ exactly the same technique, and they do find again high magnetic fields associated with coronal rain.
Okay. No, because it's a very interesting observation. So, you know, even, you know, despite all the, you know, the constraints in terms of sync, etc., they are very important to, I think, to pursue them as much as possible.
Yeah, I assume you guys will participate in sort of this campaign opportunities with probe and orbiter, right?
Well, I believe that the Dan Solar Telescope participates. I think there was a NASA call a couple of years ago, or Angel, if I remember correctly, which called for participation of ground-based facilities. And I might even be a co-I in that proposal that was successful, sort of an external international co-I. It's led by Damian Christian, who is in California State University, and James Mathioudakis.
Of course, James. Yeah, I know him.
Yeah, you know, James was my PhD student. So
he was. I'm sorry.
Okay, so I don't see other raised hands. So let's thank again Mihalis for the excellent colloquium, and everybody for joining in. So that's the final Hel.A.S Colloquium for this term. So now we break for the summer. So see you in 1 month in the Hel.A.S workshop, and hopefully next autumn for new Hel.A.S colloquia. So have a nice summer, everybody. Take care.
Γεια σας, ευχαριστούμε Μιχάλη.
Γεια σας, παιδιά.
Ευχαριστούμε very much.
Ευχαριστώ πολύ. Γεια σας.
Bye.
Γεια χαρά.